Alright, let's get started. This is an introductory video to the Laplace Transform to solve a differential equation. Our differential equation is dy dt plus 7y is equal to e to the minus 6tt. And our initial condition is y of 0 equals to 0. So here's a little diagram I've got right here to explain how it works in a simple way. So we have a function f of t. We take the Laplace transform of the entire equation. It is now in the S domain. We solve for y sub s with algebra. And now this could also be denoted as fs more generally, but it also could be denoted as xs. It really depends on the variable you're trying to solve for. This could be dx dt, it could be df dt or dy dt. But I use fs usually because it's more obvious, because everything's like in a term like a f of this means function, right? By the way, just notation wise, see how this is lowercase and this is capital F? So if it's in the S domain, you would capitalize the letter that's denoting the function, whereas in the real domain, which is not the S domain, the time domain, you would have it lowercase f. So that's the way it goes. So f of t, you take the Laplace transform, you have it in the S domain, you solve for y sub s, and then you take the inverse Laplace transform, more algebra, and when you finally apply the inverse Laplace transform rules, you'll get to f of t. So that's pretty much the gist of it. So let's get started. So before I get started, I'll just explain that, well, we already know that the Laplace transform of f of t is equal to fs, right? So the problem with taking the Laplace transform with a differential equation is, well, how do you take the Laplace transform of a derivative? If you want to take the Laplace transform of a derivative, it follows a pattern, but for this video, I am only going to show just these two rules, seeing as we only are dealing with the first derivative. But the Laplace transform to solve a differential equation is merely just another method to solve a differential equation. This is an alternative to either an exact equation, separable differential equations, linear differential equations, homogeneous differential equations. You get the gist. So it's basically another method. And the cool thing about the Laplace transform is that it automatically turns it into like an algebraic equation. And the reason why that's so great as well is because the reason why the Laplace transform is also superior to solving differential equations, because if you've noticed from the derivative, you can automatically plug in your initial conditions once you take the Laplace transform from the very first step. So that's a really key feature of the Laplace transform. So let's get started. So I'm going to take the transform of the entire equation. So dy dt plus 7y is equal to the Laplace transform of e to the minus 6t t. Now, we already know how to take the Laplace transform of dy dt. That's just s ys. I'm using y of s because we're dealing with y. It depends on the equation you're dealing with. So sys plus 7ys equals. Now, what's the Laplace transform of this? Well, this looks like to me, I already know the answer to it, but I'm just going to write it down to save time. If you don't know how to take the Laplace transform of anything, I'll probably start making videos on how to do that. But you generally just follow a table, unless you want to follow the rigorous definition, which nobody in the world wants to do. But I will eventually try and get around to that. So this is going to be s plus 6 squared. That's the answer to that. So remember the steps. I have now just taken the Laplace transform and it's now in the S domain. I made a huge mistake. I didn't actually follow the formula. There's supposed to be a minus y of 0 here, but it does not matter because y of 0 is 0. So I'm literally just going to be writing minus 0. So I'm very sorry about that mistake. So yeah, sys minus 0 plus 7ys. It doesn't actually change the equation. Alright, so now I want to solve for ys. Well, in this example, it doesn't change the equation. In other examples, it will. Ys s plus 7 is therefore equal to 1 over s plus 6 squared. So therefore ys is equal to 1 over s plus 6 squared s plus 7. And now, because I've got ys on its own, I can go back to the first step. I've solved for ys with algebra. Now I take the inverse Laplace transform. And all I did in this step was factor out ys. See, I have an s term attached to ys and a 7 attached to ys. So that's why ys is factored out here. And then I just divided both equations by s plus 7. And now I have ys is equal to 1 over s plus 6 all squared times s plus 7. Now I'm going to take the inverse Laplace transform of both equations. And obviously this video is slightly too long. I know this equation is actually going to take me a tiny little bit of time to solve. So I'm going to finish solving this equation in the next video. In the next video, it's merely just me solving for the inverse Laplace transform of this. Thanks for watching, and I cannot believe that I made this slip up here. Just follow the rules, these two rules here, for first derivatives, and you'll be fine. Well, first derivative and just the function. Anyway, I'll see you in the next video, and I plan on making videos mostly centered around the second derivative for the Laplace transform. Yeah, and I will probably do 1 or 2 videos on the third derivative. And the reason why I'm not doing much focus on the third derivative is because the third derivative should only be used to strengthen your skills using the Laplace transform to solve differential equations. The third derivative is not something that you will see most commonly in your course. It's not something you'll see on an exam, mostly because it's either too lengthy or it's too hard to solve for the average person, and there's much more better uses of your time. Yeah. Anyway, see you in the next one.